So unlike several talks that happened in yesterday and today, I'm a theoretician, so my talk may not have the products or something, but it will have a product of its own kind. And till yesterday, I had a completely different set of slides that I thought I will talk. I thought that I will give a gentle introduction to parameterized complexity. But looking at the audience and the way other speakers went around, I thought that I will try to motivate this. So 2013 or 14, we were in the Brown University, and we were writing this book on parameterized algorithms. And suddenly we talked about, so if I find someone in elevator, what is the pitch I can give about the field? So we finally, after a lot of discussions, we thought that here's one cute algorithm that I can teach. I believe if anyone with a slight understanding of little bit of probability and algorithms, or at least who has seen a bit of undergraduate algorithms, I would be able to motivate and tell him about this field. So that is what is going to constitute the first few minutes, and I hope you will be able to follow that up. And after that, I will tell you a little bit of what I have been doing, or what the few gems that the field has been able to produce over the last 2.5 to 3 decades. So that is what. So as my title says, it is about bad algorithms. So I will explain why I call it bad algorithms, because this is how it has been traditionally called. Or rather, let's say I'm going to talk about bad algorithms which are good. I mean, you can also say like advantage on bad algorithms. So whatever you feel like, I mean, you can take it up. So let me acknowledge, so some of the slides that I picked up was from this by Kevin Van, who has this algorithm course based on algorithm designed by Kleinberg and Eva Tardos. And it was on purpose so that people who have seen this book or who have read it, they will find it that this is what I'm talking about. And I also took some help from my colleagues, Daniel from UCST and Vera from BG, with slides and how to phrase this talk to such a diverse audience. So with that, so here's the undirected graphs. I hope everybody knows there are vertices, there are edges. And so this is the slide from Vence. And, but one thing which I will need is like, all of you have seen networks and everything. So one definition that I would need going forward is a path. So path is basically a sequence of vertices which are connected by edges, or these lines that you see, and which in a lot of internet and this, you know, these hops and everything. And the number of hops or number of edges is called the length of a path. So that's all that, at least for first 15 minutes, that's all that you need. That's the only definition that I need. So here's my first question. If I give you a graph G and a number K, and if I ask you, does G have a path on at most K vertices, say K equal to 5? Can you answer quickly? Just check whether the graph has edge or vertex or not. That's all that you need. So in constant time, you can answer this. I'm not asking, I said at most 5. So, I mean, if they're given an edge or this, your answer is yes. So, very trivial question. So let's make it slightly interesting. Now I give you two vertices, S and T, and I ask you, does there exist a path on at most, say, 3 vertices in this graph, right? So here is 1, 2, 3. But in general, so this is K equal to 3 vertices, right? But this has 1, 2, 3, 4 vertices. So there is a path, but maybe there is hidden in this. So what will you do? So if you wanted to test with the graph between 2 pair of vertices, does there exist a path on certain length? What can you do? Yes, so if it's an undirected graph, all of us know the shortest path algorithm. You do BFS, Dijkstra's, Bellman-Ford, whatever you feel like, if you're weighted, unweighted. And all these algorithms runs in time some n to the power c, like c is like 2 or 3, 4, but not something that depends on k, right? Okay, so motivated by this, let's ask another question. If I ask you, does G have a path on, say, at least k vertices? Right? So it is no more at most, but maybe there's a short path, but I'm asking, is there a long path between these 2 vertices? Or in the graph. So unlike before, checking an edge or this is not enough. You might have to do more work. So for example, here's a path of length 5 in this graph, right? So this is like I'm asking for a long path in a graph. So do you think a variant of DFS, Dijkstra's, Bellman-Ford, or any of these algorithms will work? Right? Well, can we come up with any algorithm at all? So here is one algorithm that I thought of coming, is like, let's guess the k vertices, which is like n choose k, so that's n to the power k, and I then guess the ordering between these vertices, and I check whether this permutation is a valid path or not. And that is what this algorithm is going to take. And let's call this is an example of what I call brute force or trivial algorithm, that like you have a search space and you're trying all possibilities in the search space to find your object. What about, let's say, an algorithm which runs in time n to the power c, like before, here c is like 2 or 3, but not something where k is on the head of the n. Right? Can we think of any such algorithm? And if not, why not? So this is a starting point of this lecture or this talk. And so like if you look at these people, I mean, there has been from early 60s and 70s to classify problems based on how well you are able to practice, solve. And the working definition was polynomial time. So if you're given an input of size n, n squared, n3, n4, n5, this was considered good, right? And this definition is broad and robust, and it captures huge lot of problems. So for example, here's a list of problems for which we do know such an algorithm, like shortest path, satisfiability, bipartite vertex cover, matching, primality testing, linear programming, and all. But there are others, like longest path, for which probably such algorithms do not exist. So like max cut, 3 satisfiability, or vertex cover, 3-dimensional matching, factoring, integer linear programming, I mean, you name it. Okay, so basically, I mean, this idea to classify problems has been fundamental in theoretical computer science based on, I mean, how well we are able to solve them in polynomial time or not. But there are some problems for which we can actually say that you can't. For example, if you're given a constant size program and you ask, does it halt in at most k steps or not? So this is like, input has like some k plus log c bits, right? Or you are given this checker game. So these are very, very hard problem. And we do know that these problems cannot have polynomial time algorithm because some of them are, as they say, they're just very hard. They're undecidable problems in our languages. But there are a huge number of problems for which we cannot classify these things for over decades. For example, longest path. We don't know whether such an algorithm exists or such an algorithm does not exist. And here's a Karp's famous 21 NP-complete problems. Like, I mean, basically, he looked at all the good discrete combinatorial problem and he just showed all of them are hard. Meaning, which basically he said that if you had a good algorithm for any of these problems, then you will have a good algorithm for all these problems, which form the foundation of P versus NP question that we all hear all the time in theory research. Okay. So, but in 1962, Bellman, Held, Karp came up with a very good dynamic programming algorithm, which we do teach in our in our basic algorithm course, that longest cycle path can be solved in time 2 power n, n square, and this much space. So this is what I call example of a non-trivial algorithm, because in general, if my k was like n, I'm asking, is there a Hamiltonian path or Hamiltonian cycle? And the brute force answer is try all possibilities, which is like n factorial. But this is a great saving from n factorial to 2 power n. So n to the power n to 2 power n. So this is an example of a non-trivial algorithm because you are not looking at every possible element in your search space. Okay. So for good is polynomial and bad is super polynomial. So in this talk, I'm only going to talk about super polynomial time algorithms. Okay. So fine, so let's ask this question, what about coming up with an algorithm which is n to the power, say c is like 2 and k is some huge number. I mean, there's no great thought in writing this number. It just came in the queue and I just pressed it. So now I'm asking a slightly different question. I'm asking you that maybe, I don't know about in general, but if I gave you k very big constant, can you come up with an algorithm like this? And what am I hiding? If at all, if such an algorithm can be made, what am I hiding? So computer scientists have made this big O, which hides everything if it is constant. right? So I'm not telling you what is hidden here. All I'm telling you that if you want to design an algorithm for this, I give you ability to come up with any constant here, but dependence on your input size is fixed, like 2, 3, 4, whatever. But maybe if you're trying to find a 100 size path, I allow you to have a constant that depends on 100. If you're trying to find a 10,000 length path, I allow you to have a constant which depends on 10,000. So that's the power of polynomial time algorithm that I want to use. In general, n will be much, much greater than k. Of course, it will, so if k is large, then your big O is bad, right? But if k is constant, I'm still good, right? Okay. So let's see. Up to 100, 200, depends on what the constant, what the function that governs the constant is. If the constant is like 1.25 to the power k, or the constant is like 2 power k, up to 100 values of k, you'll be able to do things. Yes, database query scheme. So like that is a P space complete problem. But imagine that if I give you an algorithm which depends on 2 to the power depth of the query. For like if you have a big database and you want to search a query, right? So if you use the length of the query, then you know this is a P space complete problem. So you do not expect. But imagine that in practice, when you are doing a query, what is the depth of this quantifier, some 4, 5, 6. So if I have 2 power d depth times n algorithm, in general, in practice, it might work very well. Okay? So I hope I have motivated you why some of this, and also this like, just by own mathematical curiosity, why such an algorithms even exist is not clear. And when such algorithms exist, when such algorithms do not exist, is what a lot of researchers deal with. And I will tell you, so here's a technique called color coding. And I will give you a randomized algorithm using this. And it was first given in 1994, 95 by Allen Student-Zwick. And so this is what, if I had to tell someone on my left, this is what algorithm I'm going to tell people. So what is so here's my color set, 1 to k. So I want to find path on k vertices. So what I do, I randomly assign a color to my graph, to my vertices. So like I go to every node and I assign one number from 1 to k uniformly at random. So with probability 1 over k, one of the integer from 1 to k is assigned. So, and now I'm asking, does there exist a colorful solution? What I mean that I'm no more looking for k path, but I'm looking for a k path that consists of nodes with distinct color. No color is repeated, right? So for example, look at this. So this is green, blue, yellow, and purple, and some light shade of green. Okay? Ignore those. I don't care whether green comes first. All I care is there a colorful where colors are distinctly used. Okay? So we are also happy with this and with this. But we are not happy with this because there are 2 yellow repeated. So now, we have done some random assignment to vertices, and now I'm asking to find a colorful k path in this graph. Okay, so here's my algorithm. So here's a random function. So for a S set, you fix a set S on k vertices. What is the probability that all the vertices get a different color? Right? So it's very easy. So if you fix those k vertices, the allowed is like, if you look at those k vertices, k factorial permutation of these colors are allowed out of k power k. Right? So this is possible colorings of S. This is good coloring of S. So this is, if you do some Stirling approximation, this is 1 over e power k, where e is this constant in ln function. Gray. K colors. Right? Yeah, I'm only using k colors. Okay. So I'm going to repeat. A coloring is good if for your set S of the k vertices, every vertex has been assigned distinct colors. No color is repeated on those k vertices. Okay? So that's a good event. Okay, so I'm going to do some bunch of times, some e power k dot t times, pick a random function, look for a colorful path. If the algorithm finds a k path, report such a path, else you say G does not have, right? So if there is a k path, so if there is no k path, there is no way you will find a colorful k path. So this algorithm definitely reports correctly. But if there is a k path, what is the probability that algorithm will find at least one? So look, you will fail. Why will you fail? So you will fail, so you succeed with probability 1 over e power k. So you will fail with probability 1 minus 1 by e power k. And I have repeated it e power k dot t time. So what is the probability that I will fail in all those instances? Like this, so my success probability is 1 minus this, which is 1 minus 1 by e power t. So if I choose t is like some log n or something, then with very high probability, I have succeeded in finding this colorful path, right? So if you use t log square n, I mean, you can make the probability as close to 1 as possible by repeating it as t. So the only thing which is left in explaining to you, how do you find such a colorful path? And what is the running time of that? Okay, so finding a colorful k path. So if you have seen a dynamic programming on subsets of vertices for Hamiltonian cycle, it is exactly the same, but now I'm going to do dynamic programming on colors, not on the subsets of vertices. This is where I saved from n to k. So what is this? So this is a vertex v. S is subset of some 1 to k. It's true if there exist cardinality S vertices ending in way using all colors from S. So if there is some path that ends on V and uses all the colors on S, then it is true, false otherwise. Now, I'm saying that, look, if I have to, V is my ending vertex, then it must be ending at it must end at some neighbor of V, this is U in V. And now, what will I do? I will delete the colors of f of v and ask, is there a path that ends at u and uses the colors of this? If this is a path, then I append myself and I'm very happy. And since colors are distinct, this is a distinct path. So it is OR over all this. So for each neighbor u of v, is there a path ending in u? Done. So how many table entries are there? So there are 2 power k dot n table entries because there were many subsets of S. Order n time to fill each entry. So the total time is 2 power k dot n square. So this is a simple 2 power k n square algorithm to find a k path, which implies, so if I repeat e power k 100 times this, then with probability 1 minus 1 by e power 100, and this takes 2 power k dot n square time, so the total time is 2e to the power k dot n square, right? So now, if you put k equal to any constant, I have given you a n square algorithm, but if the larger path you want, of course the running time becomes worse and worse, which is expected given that till now we have not settled whether the problem is in P or problem is in NP. Okay, so that's all. That's the one algorithm that I wanted to tell you as my takeaway from this talk. Yes. Imagine this comes quite, so I will tell you with weights. So suppose you want to go to some 20 cities and you have some age weights or something, and you want to go and visit all these 20 cities, right? And you go to this planner who gives you the route to go, and you might have several things to optimize. Maybe you want to optimize, like going from here to here cost you price, or going to here cost you some distance or some time, and you still want to visit all this. That's not a shortest path, no? Right? So this is what is called this traveling salesman problem or all this. So it is, that's called, what does theory does, that if I do not able to, let's remove all the other things and see if the basic discrete problem that we can solve. So this is where you can find an application of this. So look at TSP and you will find thousands and thousands of applications. I mean, you choose, but then the algorithm will run bad than what Bellman-Karp gave, because then it will become 2e to the power k, which is like 5.7 to the power n. Why do you want to use this algorithm? But look, if I was looking for a path of at most log n, right? If you do a trivial brute force, it's like a quasi-polynomial, n to the power big O of log n, but this gives you a pure polynomial time algorithm, right? So this is what I mean that There's a good algorithm, and we are trying to force how far we can push this boundary of good algorithm for what. So this is like, in some sense, we're trying to understand the slices of goodness and badness and where the boundaries lie. Oh yeah, we'll get there, hopefully at the end. But I'm not trying to teach you anything anymore, okay? So now I will give you some flavor of what happens, what is this field. So, there are NP problems, NP complete problems, but you need to solve them. So basically, a working definition could be that no algorithm solves all instances optimally in polynomial time. And now, all instances, so people have tried to remove, okay, fine, we cannot design good algorithm for all instances, but is it possible that if I restrict my input, like what about not on all graphs, but on trees, or some structured input, can we come up with an algorithm? Or you think of other way to measure your parameter, which I will come a little bit more detail, or this whole field of approximation algorithm, which says, fine, I cannot find optimally all this, but maybe I can come up with a solution that in polynomial time that is close to optimum. So if you're looking for a minimization problem, maybe 10 times the optimum, or if you're looking for a maximization problem, maybe opt by 10. So, but I have to relax something if I'm looking for a solution. So if I relax polynomial time, then if I fix polynomial time, then I relax the condition of optimality. But there are other fields like this exponential time algorithms. So like the one DP algorithm for 1962, if you read their paper, it was just like, how fast can we do if we do not want to use n factorial? So, and that has been a great algorithm from 1962, and it was improved only a little bit like in last decade or so, and I will get back to that at the end of my talk. Okay, so this is how this fields, different field has branched out by trying to cope with NP hardness in different ways. So you could come up, like there are like this average case complexity kind of thing you can come up with, and that also deals with these things in their natural way. So it's just that I didn't put it here. Okay, so I mean, what about these EG instances? We said that it does not solve all instances, but what about the EG instances? And how do we capture the notion of EG instances? So like when you structurally restrict an input, or if you take input, like a lot of algorithms that if you see, like for the secretary problem on this, it's in the random order things come, and we are able to get much better than when the worst case input, right? But so there are different ways to define the notion of easiness, and people use differently for different purposes. So parameterized algorithms defines one way to define what is the meaning of EG instances. So yes, we know that instance size is important, it matters, but is the input size or the bit size of the input is the only thing that governs the running time of an algorithm? Well, BFS, DFS, yes, we can do in linear time, but have you seen this subset sum algorithm that we teach, order n times t, where t is the target? But since it's in binary, you could have t could be 2 power n, but which can be represented using log n bits. So this algorithm in general is not polynomial as such, but if t is small, then this algorithm is polynomial. So if you try to write your running time in different forms, you might see a different governance of running time based on the, like it is, let's say, it depends on input. So like it is input sensitive in certain sense. KSAT, right? So KSAT has an algorithm with running time 2 to the power n, 1 minus 1 by KSAT. So we know that 2SAT is polynomial time, 3SAT is NP hard, 4SAT is, so as you grow 3, 4, 5, 6, they progressively becomes harder and harder, and it is, in some sense, it is captured by this running time. Or K-click, so what is click? You have this community detection and all this, right? Where you want to find K nodes such that every pair has an edge. That is what is called K-click. So only an unknown algorithm is try all possible K-size subsets and check whether there is edge between them or not. Okay? So a lot of things are important. So this is a field of parameterized complexity which was by Downey and Fellows, which measures the running time algorithm as a function of size and something else. And it is mostly applied to NP hard problems, which is like this is why I say mostly, because you can also do this for polynomial time algorithm. And this is his Downey and his Fellows who came up in early 90s who gave the theory of this field. But I must say, algorithms of these kinds have been designed way, way, way before, but people just did not have methodology to show such algorithms cannot be designed for such problems. Okay, so example for k-path we saw, right? We gave an algorithm for k-path that runs in time 2e to the power k. So we are able to write down the running time of algorithm as a function of the solution size, which is separate, and the input dependence is like really purely polynomial. So this is what is called parameterized algorithms. And so I don't care about 2e to the power k, but it is just function of something that we want. So look at another example. I will not give you the algorithm. You are given a graph G, integer k, and you are asking a question, if you have a set S, so that every edge has at least one end point in it, and its size is k. So of course, you can try all possible subsets and check whether it forms a vertex cover or not. And there are n to the power k plus 2 of them. You try all possible subsets. But this is polynomial time for every fixed k. This is what is called xp. But this is f of k n to the power gk, but there is a simple algorithm for vertex cover that runs in time 2 power k n square. So this is what we call FPT, and if you cannot design, so this is like n depends on g of k, this is not an FPT algorithm because the governance of the parameter is sitting on the head of the input size. So we just want to remove that, and that's the whole game that we play in the field. Okay, so whatever little time I have, some 15 minutes, I'll give you 5 gems in parameterized complexity or some super polynomial time algorithms, and these are my subjective choices. So that's a pincher. Gem 1. So this comes from a very deep mathematical theory of graph minors, that what it says is that every yes-no graph problem where removing vertices, edges, and contracting edges can't change a no into yes has a quadratic algorithm. So look at a vertex cover. Okay? So I'll explain what I mean by this. Okay? But basically, it is an example of what I call a meta theorem, a theorem that generates theorems. So for example, a single algorithm that works for many, many problems. Okay? It's a very good, nice, big hammer for at least for classification. So this theory was developed in more than 20 papers by Roberts and Seymour to prove Wagner's conjecture. So what is Wagner's conjecture? So first let me define what subgraph contractions and minors are. H is a subgraph of G if H can be obtained from G by removing vertices or edges. So for example, here. What is contraction? H is a contraction of G if H can be obtained from G by some contracting an edge. For example, if you look at this, if you contract this, you will get this graph, right? And H is called minor of G if H is a contraction of a subgraph of G. So you start with a subgraph and you contract some set of edges. So this is a graph closure operation, right? We'll get this graph, okay? So what is Wagner's conjecture? In any infinite sequence of graphs, H1, H2, you take any infinite sequence of graph, there is a pair Hi and Hj such that Hi is a minor of Hj. So it was a very old big conjecture, and it was proved in this. So now this is what is known as graph minors theorem, that if you're given an infinite sequence of graphs, then there exist 2 graphs where one is a minor of other. Yes? Like you take any infinite number of graphs, you just start with any infinite number of graphs. Huh? Yes, it's ordered. It doesn't matter which order you take. It doesn't matter. You just write down 1, 2, 3, 4 graphs on your this, okay? Yeah, so you have sequence of numbers, right? 1, 2, 3, n, a1, a2, like that is what I mean by sequence in this. If you write this, or if you take an infinite set of graphs, there will be 2 graphs in that where one is a minor of other. Right. Yeah, okay. So basically it says there is no infinite anti-chain. And this is what goes to the word called well quasi-order, not defining any of these things. And this is the paper which actually proved the following beautiful theorem, that for every h, there is an algorithm which depends only on f of h and cubic on the input side and checks whether this graph G contains h as a minor or not. So as an outcome of proving this big 20 papers, they proved lots and lots of graph theory as well as this non-constructive, imaginative, like unimaginative algorithm for several such problems like knot detection and this. They are the only known polynomial time algorithm. No. Of course not. If you take set of all graphs, of course there will be two graphs where one is a minor of other. No, like you take any set of infinite graphs. So like, okay, it does not have to contain all the graphs. Like example, all odd numbers. That doesn't contain, right? All even numbers, or mod 5, mod 17, whatever. Okay? So what he proved for every minor closed class F, minor closed class, what is the meaning of, look at a set of graphs. If you take delete, the graph should belong to the family. If you contract an edge, graph should belong to the, these are called minor closed. For example, look at planar graphs. If you delete an edge, graphs does remain planar graph. If you take a tree, you delete an edge, graph remains a tree. If you contract an edge in a planar graph, it does remain planar. So there are huge number of graph classes which has this property. Okay. So what is forbidden minors? So forbidden minors is all those set of graphs that does not belong to this family. So you, right, exclude HI is minor. So what does this theorem prove? That look at these graphs, right? These are infinitely many graphs, right? So if you look at the smallest subset of graphs that does not belong to this, right? Then one, if it is infinite list, then there will be one which belongs to this. One will be minor of this, which basically means that you can characterize every minor closed graphs by finitely many forbidden minor. For example, planar graph has K5 and K33, right? So your graph is planar if and only if it doesn't contain K5 or K33. But this statement is true about, you look at any minor closed family of graph, so there's a list of forbidden graphs which only depends on this graph family, not on the size of the graph, right? So now we have this amazing algorithm which can check. So now if you give me some minor closed graphs, I will make a following amazing algorithm. It has hardware all the, what is it called? It has hardware all the forbidden minors, which I can do and put it here. Now when you give me a graph, all I have to do is that take each of these minor and check whether it belongs to this or not, and based on that, answer whether this belongs to my family or it does not belongs to my family, right? So for example, if I had to test planar graph, I have K5 and K3, I'll check whether K5 is a minor or not by doing this f of h times NQ algorithm. H is like 5 or 6, so it's like really NQ, and I will output whether a graph is planar or not. So now I'm telling you, take any minor closed family, for that you have an algorithm. Now you try to make your own infinitely many things. I will not go into details, but there are lots of vertex covered, feedback vertex set, tree width, theta, planarization. All these problems are minor closed. Like you want to delete few vertices to get into this class, or you want to delete some edges to get into this class. All these problems are minor closed, and you have one single hammer to turn them down. Okay, there's something called Kurzweil's theorem, which I don't know how many of you heard, which gives you one uniform algorithm for if some problem is definable in this language. In database query, a lot of these things are also used, MSO1, MSO2. So if you have some problems which are, let's say, definable in this logic, example, say if I want to say S is an independent set of J, how will I write? For all UV in S, adjacent of UV is not true because it is one of my operator. Now, optimization problem, so you want to maximize and minimize this set, sentence that G of S holds. You can actually design some linear time, these are called Seymour definable properties, and he showed that for large families of objects and graphs, you have actually a linear time algorithm which only depends on the size of the formula. Right? So you want to find maximum independent set on trees? Yes, it has a linear time algorithm. You want to find dominating set on trees? Yes, it has a linear time algorithm. Maximum matching, it has a linear time algorithm. You don't have to make any new algorithm by hand. They exist. So these are the kind of theorems which is very important and interesting on their own in the field. I will not go. This is also I will avoid. And I will go to my GEM4, okay? So it's a lower bound. So what algorithm did we talk about? Clicks, that you try all possible k-side subsets, right? And find this, right? I mean, forget about if you, like not only finding, even if you try to approximate this click, all you can do is basically try all possible subsets. I mean, you can make slightly more smarter algorithm, but basically, this is all that you can do. So let me give you some portal to this theory of lower bounds in non-polynomial world. Okay. So if we computer science were physicists, we would have long accepted P not equal to NP as a law of nature. This is not me who's saying, so Scott Aronson said that, I mean, if we were physicists, we would have believed this, but we are mathematicians, so we have to find the real truth or the real answer. And in many ways, actually, in the modern world, we have, and now what? It's in a world where P is not equal to NP, SAT can be solved in 2 power n polynomial time, but it cannot be solved in polynomial in n plus m, where n is number of variables, m is number of clauses. 3 SAT can be solved in time 1.308 to the power n, but definitely not in polynomial time. So if we believe this world of P not equal to NP, these are the conjectures that we use and we prove variety of things, right? So in the world where P not equal to NP, a dominating set of size k can be done in n power k time, an independent set of size k can be done in n to the power actually 0.79 k, and we don't know how to do better. So if you want to find a k size independent set, you don't have to try all k size subsets, you can save a little bit. That little bit is there, right? But not in polynomial time, right? But now let's assume what is a practical relevance is that, there's a dramatic difference in running times of problems we need to solve. So we need to know where my limitations are, okay? So we need these lower bounds to guide us towards what is the right kind of algorithms that we might be able to make. And this is how we use all this lower bound guides. So, but if I wanted for this n to the power k algorithm, whether we can improve or not, polynomial time world cannot be, P versus NP conjecture cannot be the real guide to show or try to do this. So indeed, so if this were a dream situation that SAT has no 1.99 to the power n poly n plus m time algorithm, maybe SAT has no 1.99 to the power n poly n time algorithm unless P equal to NP, or maybe SAT has no sub-exponential algorithm where n divided by n by log n, for example, in poly n time. So these are some dream situations, but why are the dream theorems hard to prove? Because effectively they say that if you have a fast algorithm for SAT, automatically yields even a faster algorithm for SAT. So you don't expect to be able to prove some of these things in general, okay? So why are dream theorems these dreams? So suppose someone proved one of the dream theorems, could we use them to prove more cool stuff, right? So could we use this as a starting point for my own little world? And here's one theorem which I would like to, so this was proved by Petrascu and Williams in 2010, who showed that if you look at k dominating set, so what is a dominating set? You want to find k vertices in the graph so that every vertex is either in the set or has a neighbor in it, okay? So they said that, look, you cannot have an algorithm for k greater than or equal to 3, even little bit, unless you can solve satisfiability in 2 minus delta to the power n time, right? Now, this actually establishes connection between exponential time and polynomial time algorithms, because it says finding a n to the power 2.99 algorithm that checks whether 3 vertices that dominate all vertices in graph is very difficult, maybe impossible, right? So, because if you do this, for SAT, you will be able to design an algorithm that runs in 1.99 to the power n, which we still have not achieved. So here are a lot of research direction. assuming that SAT can be solved too fast, explore the consequences. And this has been explored to the bottom. Now all these all pair shortest paths and maximum matching dynamic algorithms, all these things are based on, the lower bounds are based on some of these conjectures from non-polynomial time world. Why is this worthwhile? For the same reason NP completeness is worthwhile. It's not that we proved anything. We just assume this, and basing this, we have been proving a lot of cool stuff. So, and even if you're disproving P equal to naught, NP would be so amazingly super awesome that you wouldn't care about what all things you proved, assuming that it, right? And if you showed that it would be a super awesome that we would not care about all the things we proved, assuming it. If you can show that SAT does not have such an algorithm. So in either case, we would be happy. So let's not care. Okay, so the last thing, so I told you, this is how one of these results are used to show that, forget about this, you cannot even approximate clique if you assume one of these conjectures. So these are the foundation for, let's say, so assuming different running time for SAT or 3-SAT forms the foundation for showing lower bounds in the world of non-polynomial time world. Okay, and here's my last one. So in 2010, we came up with an algorithm which showed that for some of the problems, you cannot have some kind of algorithms, and we were not able to prove that for some problems we can come up with such reductions. And that led people to design an algorithm for this, and they actually managed to design algorithms. So we were not fools to not make reduction, it's just that this algorithms existed. So how does it work is like counting modulo 2. So you want to count number, you don't want to count all Hamiltonian paths, but you want to count Hamiltonian paths modulo 2. Is it odd or is it even? That seems an easier task. And that led, so after 1962, there was a paper called by Bjorklund in Fox 2010, which called Determinant Sum for Undirected Hamiltonicity. Okay? So this paper presented the first 1.66 to the power n algorithm using this very cool trick of randomization, Schwarz-Zippel, and isolation, all that. Deterministic, we still do not know that we can get better than 2 power n. It's still open. Later, for k path, they got 1.66 to the power k randomized algorithm, which still happens to be the fastest algorithm known till date. So this is the 4 or 5 things that I wanted to tell you around here. And there are more things like connections to approximation scheme, FPT approximation, connections to polynomial time, how this n to the power c, can you do something about this or not? So there are a lot of other things which I am not going into, and that just concludes my, thank you.